The next problem is the vapor pressure of liquid decant is 10 torr at 55 degrees Celsius temperature and 400 torr at 150.6 degrees Celsius. Calculate delta H, delta S at 100 degrees Celsius and its normal boiling point. So, the problem number 10 says the vapor pressure of liquid decant is 10 torr at 55 degrees Celsius and 400 torr at 150.6 degrees Celsius. We need to calculate delta H, delta S at 100 degrees Celsius and its normal boiling point. Okay. So, how do we solve it? So, for liquid vapor equilibrium, can write log P2 by P1 cos 2 delta HV by 2.303 R 1 by T1 minus 1 by T2, or we can put the values of P2, P1 and T1 and T2, we can calculate delta H. So, log 400 by 10 equals to delta H V by 2.303 R. T1 is our 55 degrees Celsius. So, we can write 3828.7 minus 423.6, 328 and 423.6. So, if you further simplify this one, we get delta HV is 45 kilojoule, and delta SV is nothing but delta HV by T at boiling point. So, we get delta SV equals to 45 by temperature is 100 degrees Celsius. So, 373. So, this is joule per Kelvin. So, we get 120.67 joule per Kelvin. This is a very simple problem. Next is, so the next problem, the variation of vapor pressure in mm mercury with temperature, with absolute temperature for a given species is given by for a given species M, suppose. So, plus minus 2460 by T plus 6.69 for liquid M, and log P equals to minus 6947 by T plus 10.8 for solid M. Okay, so calculate the temperature and pressure corresponding to the triple point of substance M. So, we can replace this species by substance. So, problem number 11 is the variation of vapor pressure in mmHg with absolute temperature for a given substance M is given by log P equals to 2460 by T plus 6.69 for liquid M, and log P equals to minus 6947 by T plus 10.8 for solid M. Calculate the temperature and pressure corresponding to the triple point of substance N. So, at triple point in pressure temperature diagram, at triple point all three coexistence line they meet here. Okay, so, this is the common point for all these three lines. Okay. Thus, we can write at triple point the vapor pressure of liquid and solid states of substance M are identical or are equal. So, we can write, or hence can write so, if we solve it, we get T equals to 1091.7 Kelvin. So, this is the temperature of the triple point. Okay. So, the pressure of the triple point we can easily calculate if we substitute the value of triple point temperature to any of the above two expressions. Okay. So, on substituting the value of T in any of the above two expressions, we get P equals to 2732.3.11 mm of Hg, or you can write 35.95 atmosphere. Now, problem 12, it is very simple problem. predict whether it is possible or not to reduce magnesium oxide using carbon at 298 K temperature according to the equation or according to the reaction MgO solid plus carbon solid gives magnesium solid plus carbon monoxide gas. Delta H naught R is 491.18 kilojoule mole to the minus 1 and delta S naught R is 197.67 joule per Kelvin per mole. If not, if the reaction does not happen at or does not occur at or does not take place at 298 Kelvin temperature, then if not at what temperature the reaction becomes spontaneous. So, problem number 12 states predict it is possible or not to reduce magnesium oxide using carbon at 298 Kelvin temperature according to the reaction MgO solid plus carbon solid gives Mg solid plus carbon monoxide gas, and delta H naught is 491.18 kilojoule per mole and delta S naught is 197.67 joule per Kelvin per mole. If the reaction does not take place at 298 Kelvin temperature, then at what temperature the reaction becomes spontaneous, okay? Or what is the threshold temperature above which the reaction will become spontaneous. Okay, so first we need to check whether at 298 Kelvin temperature the reaction is feasible or not. So, it is very easy to check because we need to, in order to check whether the reaction is feasible or not, we need to calculate change in Gibbs free energy. Okay. So, delta H naught we need to calculate. So, delta G naught we need to calculate. So, delta G naught R is delta H naught R minus T delta S naught R. If delta G naught R is negative, then the reaction is feasible. So, at 298 K temperature, delta G naught R is 491.18 times 1000 joule per mole minus 298 times 197.67 joule per mole. So, you get delta G naught is 432.28 kilojoule. Okay. So, the reaction, so the value of delta G naught is positive, this is greater than 0. So, the reaction is not feasible at 298 K temperature. So, the next part is we need to calculate the minimum temperature required to carry out this reaction. Okay. So, delta or T we need to calculate. T is delta H naught minus delta H naught. Okay. So, to have delta G naught R is negative, we need to have temperature. Okay, so because delta G naught is delta H naught, delta H naught R minus T delta S naught R. So, at equilibrium, this is 0, delta G naught R is 0. So, this gives T is so, if we substitute the values, we get this is in Kelvin unit. So, if we solve it, we get T is value of T is 2484 times 0.8 Kelvin. Okay, so, this is the temperature at which there is an equilibrium in this reaction. Okay, so, above this temperature the reaction will be feasible. So, to have delta G naught less than equals to 0, we need to have temperature greater than thus above 2484.8 Kelvin temperature, the above reaction is feasible. Next we discuss another problem, problem number 13 is for 1 mole of van der Waals gas undergoing a reversible isothermal expansion from a volume V1 to volume to a final volume V2, so that the heat transferred Q is given by Q equals to RT ln V2 minus B by V1 minus B. So, the process is a reversible isothermal expansion. Gas is van der Waals gas, and so for 1 mole of van der Waals gas, for 1 mole of van der Waals gas, we can write P is P plus n square A. So, 1 square A by V square times V minus n, n is 1 times V equals to n RT. So, 1 times RT. So, for 1 mole of van der Waals gas, we get the equation of state is like P plus A by V square times V minus B equals to RT. So, we get P is RT by V minus B minus A by V square. So, this is the expression for pressure for 1 mole of van der Waals gas. So, we can write del P by del T at constant volume is R by V minus B. So, heat transferred Q is del Q is T ds. We can write Q is T ds. So, we can write Q is T is nothing but T ds is nothing but del P by del T constant volume times dV. So, we can write Q is T, since the process is isothermal one, so temperature is constant, so we can take it out. So, we get volume changes from V1 to V2 T R by V minus B times dV, and if we simplify this, we get Q is RT ln V2 minus B by V1 minus B. Okay, this is proved. We will solve one more analytical problem. So, problem number 14 is a gas obeys the equation of state PV by RT PV by RT equals to 1 plus P times B, which is function of temperature. Okay, so a gas obeys the equation of state PV by RT equals to 1 plus P times B function of T, where B is BT is a function of temperature only. So that Cp minus Cv equals to minus RT P del 2 by del T2 Bt, where Cp, okay, this is Cp minus Cp not Cv, Cp minus Cp naught. Where Cp naught is the value of Cp at some reference temperature. So, the problem number 14 is a gas obeys the equation of state PV by RT equals to 1 plus P times Bt, where Bt is a function of temperature only. So, that Cp minus Cp naught equals to minus RTP, RT times P del 2 by del T2 times Bt, where Cp naught is the value of Cp at some reference temperature. Now, solution. So, del Cp by del P so we know this one, del Cp by del P equals to minus T del 2V by del T 2P. So, we get Cp so this is the expression for Cp. Now, PV by RT equals to 1 plus P function of P times B. So, we get V is RT by P plus RT by P if we take out. So, RT by T times 1 plus P times Bt. So, we can write del V by del T at constant pressure is R by P times plus 1 plus Pb times T plus T by P times P del Bt by del T at constant pressure. So, we can further simplify, like if we do del 2V by del T2 constant pressure, we get R del 2 by T2 times Bt. Okay, so Cp is minus T del 2 by del T2 Pt dP. So we get minus RT T2 by dt2 Bt times dP. So this is the value of Cp. So we get Cp is minus RT d2 by dt2 times Bt plus constant, right. So next we consider when P goes to 0, Cp goes to Cp naught. So we get constant term of above expression is nothing but Cp naught. Okay, so we get Cp is minus RT P d2 by dt2 times Bt plus Cp naught. So we get Cp minus Cp naught goes to minus RT P d2t d2 by dt2 times Bt. Okay. So it's not a very easy problem, but it can be doable. Okay, but it's very important to learn this thing. Next is another analytical problem. So problem number 15. A substance expands in such a manner that its elasticity is equal to the sum of isothermal and adiabatic elasticities. Find the specific heat of the substance under the condition in terms of Cp and Cv under this condition. Okay, the solution is let Ca be the specific heat of the substance under the given condition So, Ca is T times del S by del T at constant A. Okay. So, we can write Ca equals to T times del S by del P So, we can write del S T times del S by del T, like T times del S by del P at constant volume times dP plus del S by del V constant P times dV by del T by del P at constant volume times dP plus del T by del V at constant volume dV. If that is the case, if we simplify further, we get equals to T times del S by del P at constant volume times del P by del V at constant A plus del S by del V at constant P by del T by del P at constant volume times del P by del V at constant A plus del T by del V at constant P. Okay. So, next it is given that del P by del V at constant A equals to del P by del V at constant T plus del P by del V at constant S. So, we can write Ca equals to T times del S by del P at constant volume times del P by del V constant temperature plus del P by del V constant S plus del S by del V constant P by del T by del P at constant volume times del P by del V at constant temperature plus del P by del V constant S plus del T by del V at constant P. So, we can write Ca equals to T times del S by del P at constant volume times del P by del V at constant temperature plus del S by del P at constant volume times del P by del V at constant S plus del S by del V at constant P by del T by del P constant volume times del P by del V constant temperature plus del T by del P at constant volume So, this is the value of Ca. But we know from reciprocity theorem. It's very easy theorem. You can always learn that. We can write del S by del P at constant volume is del P by del V. Constant S is minus del S by del V at constant P, and del T by del P at constant volume times del P by del V at constant temperature equals to minus del T by del V at constant pressure. So, we can write, so Ca equals to T times del S by del P at constant volume Thus, we get Ca equals to T times del S by del P at constant volume times del P by del V at constant temperature minus del S by del V at constant pressure plus del S by del V at constant pressure. So, these and these get cancelled, and in the denominator we get del T by del P time at constant volume times del P by del V at constant S minus del T by del V at constant pressure plus del T by del V at constant pressure. So, they get cancelled here. So, we get Ca equals to T times del S by del P at constant volume by del T by del P at constant volume times del P by del V at constant temperature by del P by del V at constant S. So, we get Ca equals to T times del S by del T at constant volume times isothermal elasticity. Okay, so we can write Ca equals to T times del S by del T at constant volume times isothermal elasticity by adiabatic elasticity. So, we get Ca equals to Cv times Cv by Cp. So, we get Ca equals to Cv to the 2 by Cp. Okay, it's very it's a bit difficult problem. You need to really understand the things, then only you can solve it. Okay, so but you can always try it. Okay. So, problem number 16. Compute the slopes of the vaporization and the sublimation curves for H2O at 0 degree Celsius from the given data and so that they are two different lines and not two parts of the same line. Given the latent heat of vaporization is 607 calorie and the latent heat of sublimation is 687 calorie. Consider volume of gas minus volume of liquid equals to volume of gas minus volume of solid equals to 21 times 10 to the 4 centimeter to the 3. This problem is based on phase rule problem. It says compute the slopes of vaporization and the sublimation curves for H2 at 0 degree Celsius from the given data and so that they are two different lines and not two parts of the same line given the latent heat of vaporization and the latent heat of sublimation. These are the values given and we need to consider that volume of gas minus volume of liquid equals to volume of gas minus volume of solid equals to 21 times 10 to the 4 centimeter to the 3. Now, the solution. From the Clapeyron equation we know, so we need to consider Clapeyron equation from the Clapeyron equation. We know dp by dt equals to delta H by T V final minus V initial. Okay. The slope of the vaporization curve at 0 degree Celsius is given by dP by dt when temperature is 273 Kelvin equals to 607 times 4.2 times 10 to the 7 by 273 times 21 times 10 to the 4, okay, as Vg minus Vl is to 21 times 10 to the 4 centimeter to the 3. Okay, so we get dP by dt is 0.337 mm of Hg per degree Celsius. So, this is the value of dP by dt for the vaporization curve. Okay. So, for the vaporization curve, the slope is 0.337 millimeter of Hg per degree Celsius. Now, the slope of the slope of the sublimation curve at 0 degree Celsius is given by okay. So, they are different. Okay. So, the slope of the vaporization curve is different from that of the sublimation curve. Okay. So, the sublimation curve is thus steeper than the vaporization curve at 0 degree Celsius temperature. So, they are two different lines and not the two parts of the same line. Okay, so, since the slopes are different, so they are two parts. They are two different lines, not the same part of the line. Okay. Next, problem number 17. Find the thermal efficiency of a reversible engine operating in a cycle consisting of two isotherms and two isobars. Using using ideal gas as working substance. Assume the specific heats Cp and Cv to be constant throughout the process. So, it says find the thermal efficiency of a reversible engine operating in a cycle consisting of two isotherms. Isotherms means temperature is constant or temperature is fixed, there is no change in temperature, and two isobars means pressure is fixed. Using ideal gas as working substance, assume the specific heat Cp and Cv are constant throughout the process. Okay, so, if we need to consider this diagram. We need to consider this pressure volume diagram. Okay. So, here pressure is constant, process 1 to state 1 to 2 and state 3 to 4. Okay, so, this is the cycle we need to consider. So, it goes from state 1 to state 2, then from state 2 to state 3, and from state 3 to state 4, and it comes back again to from state 4 to state 1. Okay, so, what is the solution? Okay. So, solution of this problem. The thermal efficiency eta is 1 minus Q2 by Q1, and Q1 is Cp times T1 minus T2 plus R T1 ln V3 by V2, or you can write Q1 equals to Cp times T1 minus T2 plus R T1 ln P1 by P2. This is because as P1 V2 equals to P2 V3. So, you can similarly you can write Q3 or Q2 equals to Cp T1 minus T2 plus RT2 ln V4 by V1. So, you can write Q2 is Cp times T1 minus T2 plus RT2 ln P1 by P2 as P1 V1 equals to P2 V4, right. So, we have got the value of Q1 and Q2. So, we need to calculate now eta. So, eta is 1 minus, now we substitute the value of Q1 and Q2, we get eta is Cp times T1 minus T2 plus RT2 ln P1 by P2 by Cp times T1 minus T2 plus RT1 ln P1 by P2. Okay. So, if we simplify further, we get eta is, we get eta is R T1 minus T2 plus or times ln P1 by P2 by Cp times T1 minus T2 plus R T1 ln P1 by P2. Okay, so this is the solution. Next problem 18 is 1 mole of O2 escapes adiabatically into an evacuated chamber of such size that its final volume is 10 times to that of initial volume. Given that Cv equals to 4.90 calorie and A for oxygen is 1.36 atmosphere liter to the 2 mole to the minus 2, calculate delta S if the initial temperature is 0 degree Celsius. For volume calculation, use ideal gas equation. So, again this is an interesting problem. 1 mole of oxygen escapes adiabatically into an evacuated chamber of such size that its final volume is 10 times to that of initial volume. Given that Cv equals to 4.9 calorie and A for oxygen is 1.36 atmosphere liter to the 2 mole to the minus 2, calculate delta S if the initial temperature is 0 degree Celsius. So, solution is, so we have here one chamber free expansion and we get number of mole is 1, final volume is V2 equals to 10 V. Okay. So, it is an example of free expansion. Okay. So, it is an example of free expansion. So, the initial volume of the gas O2, we see this is V1 is nRT by P, and V1 equals to V equals to 1 mole times 0.08206 liter atmosphere to the atmosphere Kelvin to the minus 1 mole to the minus 1 times 273 K by P is 1 atmosphere. So, you get V equals to 22.4 liter. Now, we know that integral of times dV equals to V1 by V1 to V2 A by V square dV. So, we get A V2 minus V1 by V1 times V2. So, we get A times 9V by 10V square. Okay. So, we get 1.36 times 9 by 10 times 22.4 liter atmosphere. Okay. Again, delta U is NCV T1 minus T2 minus 1.36 times 9 by 10 times 22.4 times 24.21 Kelvin. Now, the given problem is an example of adiabatic and free expansion. So, Q equals to 0 and W equals to 0, hence delta U equals to 0. So, we can write NCV T1 minus T2 minus 1.36 times 9 times 24.21 by 10 times 22.4. Okay. So, T1 is goes to 0. So, putting the value of, so since T1 equals to 0 degrees Celsius means 273 K. So, we get T2 equals to 272.73 Kelvin. Okay. So, what is the value of entropy change? Okay. So, delta S is NCV ln T2 by T1 plus NR ln 10 or V2 by V1. So, this is the expression for entropy. So, we get delta S is 4.9 ln 272.73 by 273 plus 4.575, which is calorie per Kelvin. So, if you further solve it, we get 4.57 calorie per Kelvin, or delta S is 19.12 joule per Kelvin. Okay, so this is the value of entropy change for this process. Thank you.